Welcome back. In this lecture, we are going to talk about dynamic refined mesh library. In OpenFOAM, we do not have an option of remeshing. We can either move the mesh points or we can refine. Here you can see that these particular mesh elements, they are going to refine as the velocity gradient is above certain threshold that we have set. You can see as the flow progresses, the velocity gradient changes and accordingly remeshing is going on. In this particular lecture, we are going to talk about that how we can use remeshing in our simulations which require finer resolution as the flow progresses. Let's observe this simulation. It has refined this entire domain wherever the velocity gradient magnitude is above certain threshold. Here we are showing the vorticity magnitude of the flow. You can see it refines according to the need. In this way, the accuracy is better compared to if we have a uniform resolution everywhere. That also saves the computational cost. With this, let's start this lecture. We'll start with what we have done in the previous lecture. We'll pick that particular simulation which is flow past a square cylinder. We'll see that how we can change that moving mesh to a dynamic refinement simulation. First of all, let me first copy the previous simulation. I have copied the simulation here. Let's look at the simulation. Here we had this particular square cylinder, and this using certain library was moving this patch in certain direction. You can see this that the mesh points are distorted due to this particular motion. Let me run this again. Now we'll take this particular simulation and we'll see that how we can modify this such that we can have mesh refinement here. Then we'll see that how we can merge these two mesh motion with the mesh refinement in OpenFOAM. First, let me tell you that if you have a tet mesh, then you cannot have refinement in OpenFOAM. You should have a quad mesh. Basically, this triangular mesh, the OpenFOAM library looks for 8-point cells, which are the quad mesh or hex mesh in 3D. Therefore, we are going to edit this to make sure that we have a mesh which has all hex elements, not tetra or some other shape. Let me open Visual Studio and edit this. Here we have that entire thing. Let me remove all the outputs first. Now let's look at these files. Right now we are generating everything using Gmesh, which creates triangulation as well as quad. But now we are going to use a block mesh for that. Let's create a block mesh. Creating a block mesh is easy. Let's do that. If you are not sure that how to create a block mesh, you can go to one of the lectures on turbulence modeling on our YouTube channel. There you can see that how to create block, how to set things to set the gradual refinement of the mesh. We are going to use the following dimensions. These coordinates are the endpoints of the bigger domain, which are the bounds of the flow. We are going to use these coordinates. These will remain the same. We will have say 91 or say 100 points along the x direction. We'll have the empty boundary condition along y, and along this we'll have say 60 partitions. We'll have simple grading here, and then we'll use SnappyHexMesh to create the mesh around this. For the boundary condition, we'll have these patches. All of them are of type patch. Once this is done, then we can block mesh and see if we have what we need. So there was some error. Let's see what is the error. So these are not the boundary, these are patches. Once this is done, let's see what we have now. We have a block. Inside this we have to keep one square cylinder. Let's create that square cylinder. For this we have to create one more file, which is, let's say, square only dot. The dimension of that square is as follows. So we are going to keep a mesh size of 0.005. Radius is this and the height is 0.15. Then we'll create all the points and then we can easily join them because we only have 4 points. We have 4 to 3, then 3 to 5, then 5 to 2, then 2 to 4. Then we need to extrude. We also know the command for extrusion, but we can always go to Gmesh and open square only. We have this, and then we can extrude in this direction. We'll choose this and then extrude, translate, and then in the y direction we should have negative 0.30. This should be 0, and we do not need any mesh. And let's select this, and then we can do 2D meshing and then export this STL file. We can keep a key or binary, doesn't matter, and then close. So now we can check in parafoam that where that cylinder has been created. You can see the square cylinder will be here, and I will use SnappyHexMesh to resolve this. Here we can see right now the resolution is something like this. So let's go back and let me first create a file, SnappyHexMesh Dict. This particular file you can find in any of the tutorials. Here we should have a cylinder.stl in the tri-surface folder. Let's copy this. First let's check the surface check, and f_stl. It is not closed, that we know, but there is no other problem apart from that. Now we'll copy the square.stl in constant, then tri-surface. There is no folders. Let's make tri-surface folder, stl to constant tri-surface and cylinder.stl. Now we have this cylinder.stl where we want it, and these all things you can set. Minimum refinement cell is set to 10. The n cell between levels is 2. There will be 2 cells between 2 different levels. The minimum thickness between of a layer. Then if you have any features you can put here. If you have any refinement surface, we have cylinder, you can set the refinement on the surface here. This will, for the current refinement, it will divide it by 2. There will be 1 layer of refinement. If I set this to 3, then there will be 3 layers of refinement. Then the resolve feature angle, you can set this to make sure that whatever angle you set is resolved properly. And then you can have also this refinement region, which is set for the cylinder only. According to this, it has chosen a distance. For this distance, it will choose this particular refinement. And then location in the mesh. This you should mention to make sure that it knows that which is the interior and which is the exterior for the CFD analysis. Then we have snap control. In snap control, it snaps the intersection between the hex that are generated and the surface of the STL. There will be smoothing iterations. The tolerance is set to this, and there are various other things. The most important thing is you can turn on and off some of the operations. These two are very important. Add layer is required when you want to make sure that up to some thickness you want very fine resolution. Then you cannot do that with the help of castellation. You have to use layers. So in that case, layers are helpful. Right now we are not going to use any kind of layers. You should also see that it uses a mesh quality dict to make sure there is some quality control during the mesh generation. So let me create one here. We'll use the default libraries. Now we can do SnappyHexMesh and always do an overwrite, otherwise it will create a new mesh. Now let's see the mesh. You can see there is a hole which has been created, and the mesh also has 2 layers as mentioned. Between every refinement there are at least 2 states. Now let's see we have everything else set or not. This we can remove because we don't want dynamic mesh for now. Let's rename this to old. Since we have changed the dimension by a large amount, let's change the transport properties accordingly. We have to decrease this to make sure that something will happen. These are all dummy values, but you can always calculate the Reynolds number. Also, let's reduce this because the dimension is much smaller now. And right interval, let's make it 100. These we don't have to touch for now. Let's change according to the new boundary conditions. We have sides, bottom, top, inlet, outlet, and cylinder. We have these as sides. This is top, and similarly bottom, inlet, outlet, and then cylinder. And this is inlet. Let's keep it here so that we know what is going on. So sides, top, bottom, inlet, outlet, and cylinder. In case of velocity as well, let's do the same. These are sides. This is top, bottom. Make sure that you do not have empty boundary condition where you want to do the refinement. This is running fine now. So now let's look at the results. You can see this has formed and we have stopped it. Now let's activate the dynamic mesh. The dynamicMeshDict we can activate. In the point displacement, we'll keep empty as calculated and value as 0. This one sides, then this is top and bottom. This is outlet and this is cylinder and this is inlet. Now in the U we have to set this as moving wall velocity and the value is this. And in the dynamicMeshDict, since we have changed the coordinates, we have to change these accordingly. This is now a cylinder. This is 0.1 to 0.3. Mass we can reduce to 0.229 and center of mass keep as 0, 0, 0. This we can keep as is. This also, let's change this to 0, 1, 0 and 1. And this also we have to change to along y-axis and this also along z-axis negative 0.98. Everything else can keep as is. Now this we have to keep along the x-axis. Let's change the center of rotation to 0, 0, 0 and the direction along the x-axis. And similarly this we have to change to y-axis. This axis should be 0. Similarly the vertical spring should be along 0, 0, 0. Similarly this we can reduce the magnitude little bit. Similarly for damping. And in case of axial spring, this is along the y-axis. Let's reduce the magnitude of this as well. Apart from this, we need not to change anything. And now run this again. Just make sure that you have changed the file name. And let's run this. Let's kill this and see what happened so far. So you can see this solid is moving and you can also see the motion in the mesh. This has created some nice early vortices due to this particular motion. Now we'll try to apply mesh refinement here. What we have done so far, we have tried to do the same thing that we have done using a Gmesh mesh. Using the same methodology, we had applied the same procedure to perform a mesh motion on a mesh generator using SnappyHexMesh. Now we'll do mesh refinement separately and then we'll combine these two. Let's go back here. So let's name this, copy this particular file here with rigid body and change this for the refinement. For this, we'll go back to the source code. Let me open the source code. This is the source code for OpenFOAM version 2412 from OpenCFD. So you can check which version is this by going to etc, then bash rc. This is the OpenFOAM version from OpenCFD Limited. Here you can check this is version 2412. Here, if we go to dynamicMeshDict and then go to dynamicMeshDict Refine, you can see that this is an example of the dynamicMeshDict which is given. Here you have to define the refine interval, the field which it is going to use to do the refinement, what is the lower refine level of this particular field, and what is the upper refine level. Then the buffer layers between two refinements, and then the max refine level. This number means that from the original resolution, if this is 2, then it will just divide by 2 and then perform the refinement. This is the maximum limit. If it keeps on refining, what is the maximum cells your simulation can have. In the correct fluxes, you can define some of the fluxes for which you don't want the correction. Then this is the dump level, which is by default true for all the cases. One thing to note here is that this is a derived class from dynamic motion solver list. Along with the refinement, you can also pass some of the dynamic solvers. You can have a list of motion solvers that you can have along with refinement. We'll see that after we are done with refinement. Let me close this and let me comment this, because eventually we are going to use this. I can write dynamic refine FEMesh, and then I can define the coefficients. Coefficients will be the same that we have seen in the source code. These are the coefficients that we are going to use. The field here in this flow past a square cylinder is velocity gradient. Since we do not have this particular field, therefore we'll pre-process this. So in order to do so, we'll go to control dict and create a function here. This one is a function of type coded. Here you can see that this is the library it is using, utility function object. This is the most important part, that you have to write the code in the code execute. This will make sure that the execution is taking place every time step. And the execution interval you can set. This should remain 1 so that you have velocity magnitude updated after each and every time step. This is how you write the code. You can call the mesh by using this function. You can see that going to the source code as well. Let me open the source code. In the source, if you go to function objects and then go to utilities, and here you go to the coded function objects. Here you can see that these are all the options that you can have in a coded function. Here we have code include, options, libs, and here you can see execute, which will call this particular function. When you go to this execute, you'll see that how it is going to call it. Post processor overrides the usual execution control behavior and forces this execution. This is used in a post processing mode. So make sure that while you are doing the refinement should be done after you need these values from the previous time step. So let's go back and we'll see once we have executed this that how we are getting this. This is a function created for you, and we use this function to access the mesh, and then we can look up any of the variables. We are looking up velocity, and then from that velocity we are again creating a volume scalar field. In the entire volume, a scalar field which is velocity gradient magnitude. The magnitude value of this is set as this. This is again calculated by this. You can just do this thing, and then you can do this check-in to make sure that it is saved. You can also print it. This is the minimal thing that you can do to create a variable which is not there in your simulation. Now let's execute this. Let me first clean everything, and then we'll also make sure that we have a correct dynamicMeshDict, which is this, and now we'll run this. It is creating the file. Once this is done, you can see what it has created. Here you can see it has created this runtime selection table. The most important part is this function which is automatically added. This is a private member function, and this is what you are calling to get the mesh. Here you can see it is saving the files. We'll wait for some time to get enough of this data. It has run for around 7.5 seconds. We'll stop here just to visualize the results. Clearly there is some refinement compared to our initial mesh. As the time progresses, the refinement is adapting to the velocity gradients that are present in the flow. Let's also look at the velocity. So you can see that from the start how it is nicely capturing because we have refinement here. Now let's try both the things together. Along with the refinement, let's add the rigid body motion. In order to do so, we can have solvers. Let me add solvers, then a custom name for this, my motion, and then we can copy everything in which we have coded for the rigid body motion. We can copy it here. We can remove these comments. There is one more thing that you should note, that this particular thing which is with motion on the patches and the refinement, it does not work well in this particular version. I did some bug fixing, so if it works for your case, then it's well and good. If it does not work for your case, you can write to me in this particular email and we can work this together. If this is done, you can go back and run this. We'll clean everything and run OpenFOAM. So we can stop here and just check the results. Here you should expect that since the body is moving, the vortices should form much before with respect to what we have seen earlier. We'll look at the surface with edges first. Let me play this. There are these kind of vortices. According to the vortices, the refinement is also adapting to that. We don't have a longer vortex. Due to the motion of this particular solid, the vortices start detaching much earlier. We can see that in the velocity plot as well. You can see from the start, since this is moving, the vortices starts detaching much earlier. We can also look at the vortex by just using a calculator. You can just type curl of u, and here we can go to the result and change it to something. Let's try a lower value, say 30, and then play this. And now we can see the vortex centers. This is the various type of refinement in case of a single phase flow, but in case of a multi-phase flow, we have a better and convenient field according to which we can refine, which is the alpha. Is the phase index. For example, alpha for water is 1 and for air it is 0. The interface where the phase is changing, there we can have some kind of refinement that we can capture the interface much better. Let's see how we can do that. We'll create another project. So let me go back and create another project. We'll call this VOF refine. Inside this, let me copy everything from our previous run, which is here. I'll copy everything to here. What we are going to simulate now is there is a box, and inside that box we have a certain part of the fluid which is at rest, and then at t equal to 0 it starts going down. This is a classic dam break problem that we are going to solve in 3D. Let's do that. I am going to use a very coarse mesh so that this is very fast. Let me remove all the files which we don't require. We also don't need this dynamic code. Let me also open this in VS Code. First thing that we have to do is create a block mesh. This block mesh, we need it from -1 to 1, z equal to -1. Then similarly, the next point will be this, and the next point will be that, and similarly this one. So let me see if the sequence is fine. Now we'll copy this and change the z value, and for x, y, z, all the directions we need 10 cells. And for patches, the top patch we are going to name this as atmosphere, and all other patch will merge to one patch, which is wall. And these all we can remove. Now let's run this. Let's see if we have the correct block mesh. We have our cube, and let's look at the edges. We have 10 edges on all sides. This is fine. Now in a similar manner we should have these. In case of multi-phase flow, we have to first set the solver. We are going to use interFOAM. This we can keep as is. We'll change if we require something. This we don't require anymore. Now what we'll do is we'll run interFOAM. Why we are doing this? Because we want to check what else do we need. First of all, in the patch field point displacement, we have to fix all the boundary conditions. Here, let's make this walls for all the walls. These point field we don't require anymore. We can remove this. And in the dynamicMeshDict, we just need the refinement. We don't need any motion. Let's remove this motion and we'll just try dynamic mesh. And now for pressure and velocity, we have only two values, walls and atmosphere. For the atmosphere, we need pressure, inlet, outlet velocity. We'll set this to uniform 0, and all our walls are no slip walls, and velocity is 0. In case of multi-phase flow, we don't have pressure. Instead of that, we have modified pressure, which we call PRGH. This we are going to keep uniformly 0 everywhere, and for the walls use fixed flux pressure, and for this we are going to use the phi as phi absolute. The value we are going to take as uniform. For the atmosphere, we are going to use total pressure, and we are going to use P0 as uniform. Apart from this, we need alpha water. Alpha water is the value which tells it that which domain is water and which is not. For this, we have to set this using set fields, but to start with, we should have some values defined. We'll use these particular values, everywhere 0, and we'll use set fields to set these values. Let me create the set fields file. In the set fields dict file, which looks something like this, you have to define a default value which will set the value of alpha water in each and every cell center, and then you can use various methods to set the value to certain region. We have used this particular region. We are using this method box to cell. Here you have to define a box. You can define by just telling it 2 points which are diagonally opposite along the face. The first point is the corner point of the domain, and another point is somewhere in the middle. This we can set as 0, 0, 0.5, 0.5 to make it a little bit interesting along the z direction. So this is fine. Here we will set the value equal to 1. Then in the schemes, we need some extra things that we are solving. For example, we should have rho phi u and the solvers for alpha and the solvers for alpha, and then for k and omega as well, but we are not going to solve any turbulence model. Our turbulence model is lambda. We don't need that. And here we should have a solver for alpha as well. We will add that. Instead of P, we should have PRGH. Similarly here, P final, we should have PRGH final, and nothing else is required. Since we are solving using Pimple, we can also have one more parameter, which is C alpha, which is by default set to 1, but we can decrease this value to make the interface between two phases sharper. Once this much is done, we can try solving this. We have done the block mesh. After that, we have to do set fields. Set fields will set the fields for this alpha water, and it has set these values in the entire domain. And then we can run interFOAM. There are some problem. Let's see in the atmosphere, 0U atmosphere. We missed this semicolon here. One more thing is in the transport properties, we should have instead of just one new, we should have phases. Let's set that as well. So these are the phases. We have two phases, air and water. We don't have to do anything for air because wherever we don't have water, we have air. Sigma is used for the surface tension effect if we have a bubble or something like that. Then let's try running again. We need G value. We can set the G value. Let's create this. We can make it along Z direction. Let's try running. There is some problem with the field pressure, don't have a correct value. When we are doing P rho GH, which is the modified pressure, we should have a different dimension, which is this. Now let's solve. Solve are not found in the dictionary for these two. We have to remove one of them. This is for RGH. And this is something which is required. We have to go to the control dict and set this to say 0.1. This is the Courant number for max alpha. This we are setting as 0.1. In the FE schemes, we missed this one as well. We have not saved it after saving, and this is something which is different. Let's copy this and use this as well. For this as well, we are going to use Gauss linear. Now it's running. This is how you can read the errors and improve your setup for OpenFOAM. Let's see the results. Let's look at alpha water. Let's try to get more points in between. I'll make this 20 and again run this. You can see that it is behaving like dam break. We have a column of water here, and then when we release it, it settles. Now if we look at the edges, it's very coarse, and if we just look at just alpha water and let's set it to 0.5 to 1, then we'll get a very coarse surface. This does not look like a natural surface. We can improve this by refining. Let's try that. We have to rename as MeshDict. Here the field is alpha water, 0 is air, and 1 is water. Anything in between you want to refine. This is how we are defining the interface. And then the undefined level is if it has refined to very high levels, then if it is less than this particular value, then it will undefine. We are basically trying to make sure that this does not affect our simulation. This is the number of buffer layers between two refinement zones and so on, as we have discussed. Now we can try. Before that, let's also try to decrease the time steps because this was causing problem. Let's decrease it by 0.1 and try again. It has run for a sufficient time now. Let me parallel look at the results as well. This is the result so far. You can clearly see that the water block is nicely refined at the interface. If I run this, you can see that the refinement tracks the interface. Wherever there is no interface, it is de-refining. We can also look at this threshold, how the water is behaving. You can see the surface is much better than before. Let me extract the surface and make it a little bit opaque, transparent, and choose a solid color here. Now you can just look at how water is behaving from the start. So you can clearly see that it is reaching up to the wall, and it has reached this particular corner and create a very unique splash from this side, which is the merge of these two splashes and as well as the water which was coming from this side. You can see that how the refinement helps. We can see the refinement levels on the threshold as well. This is how you can save your compute resources as well. With this, in this particular lecture, we have shown that how we can use refinement. We can have motion of the entire mesh as well. Motion of the entire mesh is very easy. There is one tutorial in OpenFOAM in 24.12 version. There you can have this particular block to move to and fro such that the water inside moves along due to that particular motion of the entire domain. But here I have shown along with this how can you move the patch as well if you have certain kind of motion in the patch, and then also you can have refinement in your entire domain and get accurate results. We can add different variables using which we can decide where we want the refinement and where we want the de-refinement. I hope you have learned from this particular lecture that how you can use dynamic mesh refinement in OpenFOAM. Let's meet in the next lecture. If you like the content of this channel, then please subscribe, like, and share. Thank you.